linear spring, well, let's do it this way, couple linear oscillators. Couple linear oscillators, and each of these dots was mass. Let's say all the masses are the same, like that, and that this thing is vibrating, and that each let's say that this vibration could be quantized. This vibration could be, well, I didn't say it that way exactly. I said that the phonon was a quantum of vibration, was a discrete quantity, let's say, a discrete quantity of vibration. And at the end of this thing, I talked about a frequency range. I think I drew this, or this was the oscillation of the spring system, and there was this cutoff at, I think pi over A. I hope it's pi over A. Well, anyway, well, I was thinking about other ideas, of course, and I was thinking about the excitation of the DNA. And the DNA is excited by these particles that get fired into these available states. You see, these states are, say, empty in the DNA. Now, the genetic code has fallen out, right? So there's no more vibration. Well, the particles in this compound go in and they replace these base pairs, and then the thing begins to vibrate. And then, because the thing is vibrating again, then you have this DNA, RNA, protein. See? But this is all a quantum mechanical operation. Particles come in quantized amounts, and then new particles are produced in quantized amounts. And so that this whole DNA then could be considered to be a field. Oh, I got field here. I got field there, and so this whole DNA is now a field. Well, now the question is how do we go from springs, how do we go from this spring system to a quantum field system? And the answer is, well, we try to work some kind of extension to this model so that these masses here, I can say, well, this is mass 1, or I can say this is mass 1, and this is mass 2, and this is mass 3, but I don't want to do that because I've got a long string of DNA here, and I'll just call this mass sub I, and this mass sub I minus 1, and this mass sub I plus 1. Okay? So that this is fairly general. Well, the masses, of course, are moving, you see? Well, they're supposed to be moving. They're moving if their frequency is in this range. That is, if the excitation is if the excitation is in this range, then they're vibrating with, say, frequency omega. Well, all right. So if they're vibrating, then what happens is each mass has a kinetic energy. Okay? Each mass has a kinetic energy, and we can call that kinetic energy P over, say, 2m. Square the P, sorry. P squared over 2m is the kinetic energy of each mass. So we'll put I there. Yeah, fine. And this is our kinetic energy. See? Now, the masses have this kinetic energy, but they're moving in the field, or they're moving under the action of these springs, you see. And now we can talk about the potential energy under which the masses are moving, and then we can talk about that potential energy in terms of the displacement. And yeah, here we go. This mi plus 1, say, is stretched in that direction. So then that spring, when it's extended that way, will exert a force on m sub I, and m sub I will have a force backward, that is mi minus 1 will exert a force backward. So what we have here is mi is moving under the force. Mi is being pulled that way by the motion of mi plus 1, and there's a force in the other direction which is related to this mi minus 1, and the potential energy works out to be something like, if I can remember correctly, I'll call this displacement, I don't know, Qi, and this displacement Qi plus 1, and this displacement I'll call Qi minus 1, and I can talk about the kinetic energy then as being, whoops, I don't want to do it that way. I want to do it this way, I plus 1 minus Qi all squared. See? That's the potential energy of mi under the action of mi plus 1 going this way, pulling this way, and mi minus 1 pulling backward. See? Well, now I can add the kinetic and the potential energy. I can say 1/2 Pi, where I, again, is this particle here, this mass, over 2mi plus 1/2 k Qi plus 1 minus Qi all squared, and now I'm going to sum over I and sum over I to n, where n is the number of all the masses, see? And now I've got the total energy of the system. Right? I got the total energy of the system, and I call that total energy of the system, I call it H. And H, again, then stands for the Hamiltonian. The Hamiltonian of this coupled oscillator system, this, which is modeling my linear crystal, which is the DNA, can be described to some extent as the sum of the potential energy, the sum of the kinetic energy and the sum of the potential energy. And now I've got the beginnings of my quantum field theory. This Hamiltonian is not a quantum Hamiltonian, but I can make it into a quantum Hamiltonian by fixing it up a bit. I can fix up the momentum, and I can fix up the displacement so that I can develop a quantum field theory in the future. Now you say, well, why do I have to develop a quantum field theory? Why don't I just leave it as it is? I mean, if I solve this equation, I can solve this equation, let's say, by using the Hamilton's equations. I gotta get this right, I hope. This is I, and this is I, and then this will be q dot, which means time derivative, and then I can do this, and I got qi equals to minus pi dot, and I can solve these equations, and out of that I can get this frequency, you see, and I can get it with this classical Hamiltonian, but I'm saying quantum field theory. Why would I want to do that when I can already get that oscillation? And the answer is because the quantum theory, the quantum field theory allows for, where can I put it? The quantum field theory allows for the boson and fermion statistics. The classical theory cannot account for these two different particles, and we'll have to talk about that again. Thank you.